Rates of chemical reactions, the iodine clock reaction. The objective of this experiment is to determine the rate expression for the reaction of iodide ion with peroxydisulfate ion. To accomplish this, we will use the method of initial rates to determine the order of the reaction with respect to both ions and to calculate the rate constant. There are a number of physical factors that can affect the rate of a chemical reaction. Several of these include the nature of the reactants. Are they solid, liquid, or gas? The concentration of the reactants, the temperature at which the reaction is run, and whether or not a catalyst is present. In this experiment, we will investigate the effect of reactant concentrations on the rate of reaction. The rate of a reaction is a measure of how fast reactant molecules are used up or how fast product molecules are formed. The rate will depend on the concentration of one or more reactant, and the mathematical relation between rate and concentration is known as the rate expression. For a general reaction, A plus B forming C plus D, the rate expression is expected to take the form rate is equal to K times the concentration of A to the X power times the concentration of B to the Y power. Here, X and Y are called the order of the reaction with respect to that concentration. These are generally positive integers, but please be aware that they do not necessarily have to be. The term K is called the rate constant and is a measure of how fast the reaction occurs. In this experiment, we will measure the rate of reaction of iodide ions, I-, with peroxydisulfate ions, S2O8, 2-, in aqueous solution. The reaction is 1 peroxydisulfate ion reacts with 2 iodide ions, forming molecular iodine and 2 sulfate ions. The rate will be measured as the rate of consumption of peroxydisulfate, so that the rate of disappearance of S2O8, 2-, is equal to the rate constant K times the concentration of peroxydisulfate raised to the X power times the concentration of iodide ion raised to the Y power. Our goal is to determine the values of X, Y, and K. The experiment is set up in such a way that when a certain number of moles of peroxydisulfate react, the color of the solution will change from colorless to a dark blue purplish color. The dark color is due to a reaction between molecular iodine and a starch indicator. Once all of the iodide ion has been converted to molecular iodine by 2 × 10⁻⁴ moles of peroxydisulfate ion, the I2 immediately reacts with the starch indicator, causing the solution to change color. After the color change occurs, we will add in a small aliquot of a new ion, the thiosulfate ion, S2O3, 2-. Please do not confuse the thiosulfate ion with the peroxydisulfate ion. The thiosulfate ion immediately converts the molecular iodine back to I-, according to the reaction I2 plus 2 thiosulfate ion, going to form 2 iodide ions plus S4O6, 2-. Once the I- is reformed, this resets the clock, and the reaction with the peroxydisulfate begins again. The time between each color change should be roughly equal for a given run. This video demonstrates the color change that occurs when all of the iodide ion is converted to molecular iodine. Then the thiosulfate is added, which resets the reaction and turns the solution colorless again. We will utilize the method of initial rates to determine the rate law for this reaction. In this method, we will begin with a specific concentration of each reactant. The first run will use 0.05 molar iodide ion and 0.05 molar peroxydisulfate ion. We will determine the rate for this run. Next, we will perform a run in which the iodide ion concentration stays 0.05 molar, but the peroxydisulfate ion concentration increases to 0.1 molar. The rate of this run will allow us to determine the order with respect to peroxydisulfate ion. The third run will have peroxydisulfate ion concentration back at 0.05 molar, but now the iodide ion concentration will be increased to 0.1 molar. The rate of this run will allow us to determine the order with respect to I-. Lastly, we will perform a run where the concentration of iodide is 0.025 molar and the concentration of peroxydisulfate is 0.1 molar. This rate will provide an additional data point to determine the value of the rate constant. For the method of initial rates, we must be able to measure the rate of reaction for each of the 4 runs. We will use a graphical method to determine the rate. For each run, we will make a plot. The y-axis will be the total number of moles of peroxydisulfate that have reacted. The x-axis will be the cumulative time required to react those moles. Here we see an example plot of data for one of the runs. Notice that the total number of moles of peroxydisulfate that have reacted are plotted on the y-axis, and the total time of reaction is plotted on the x-axis. I have used a ruler to draw a best fit line that falls closest to all of the data points on this plot. The slope of this line is a value that is proportional to the rate of reaction for that run. The steeper the slope, the faster the rate of reaction. This experiment will be performed virtually. A video has been made of each run. You will watch each video with a timer. This can be a cell phone timer, a stopwatch, whatever works for you. The reaction will begin as I pour the peroxydisulfate solution into the iodide solution. Once the peroxydisulfate has been added, you will start the timer. As soon as the color changes to purple, record the time. Do not reset or lap your timer. Let it continue to run. After the color change, I will add in 1 milliliter of thiosulfate solution, thus resetting the clock and changing the color back to colorless. Once the color turns purple again, record the new time. You will continue in this way until you have recorded 7 times. After this, you will repeat the process for the remaining 3 videos. In a second video, details will be given as to how you should prepare your plots. Additionally, the video will describe the instructions for converting your slope into a rate for each run, and how to use these values to calculate the order of reaction with respect to each reactant. Lastly, the second video will explain how to evaluate the rate constant for the reaction. Please have your data collected no later than the middle of next week, and let me know if you have any questions.